All right, hello class. Today we're going to be talking about section 3.8, which is on logarithmic and exponential functions. And what this basically does, I mean, we haven't talked about logs yet, but the exponential rule that we have right now, right, is that e to the y is itself times dy dx. So the derivative of e to the x is itself, the derivative of e to the stuff is itself times the derivative of the stuff. What we want to do in this section is actually extend this idea to, say, any base. All right, so let's extend this rule to, let's say, base b, or 2 to the x, or 1/2 to the x, etc. All right, so that's basically what we are going to try to extend this rule to, and then we're also going to try to find the derivative with respect to x of our logarithmic functions. Okay, so that is what we will be attacking today. All right, and to start all this off, what we're going to look at to begin with, and this may seem a little counterintuitive, but we're going to look at the derivative of the natural log of x. Okay, so we get this using implicit differentiation. All right, so this is found using implicit differentiation. Okay, mainly because when you use the limit definition, you don't really get much, right? If you set up your limit definition, right, you'd get the limit as h goes to 0 of the natural log of x plus 1 minus the natural log of x all over h. And there's not really much we can do about this, right? So what we do instead is we use implicit differentiation. This is very helpful tool in a lot of things. So what we start with is this. We start with y is equal to the natural log of x. Okay. And then we are going to apply implicit differentiation, but not just yet. All right, so what we're going to do is rewrite this using exponentials. Right? So rewrite using exponentials. So what this basically means that e to the y is equal to e to the natural log of x, which is x, as we know, right? They cancel each other out. All right, so now from here we have e to the y is equal to x, and now we'll use implicit differentiation to find dy over dx. Okay, so the derivative of e to the y is e to the y times dy dx, and the derivative of x, of course, is 1. Right, so this is actually a very simple implicit differentiation. This ends up being dy over dx is 1 over e to the y. Right? And e to the y, well, e to the y we know is x. So I'm going to put that back in. Right? And we get that this is 1 over x. So if y is the natural log of x, then dy over dx equals 1 over x. So what we've basically found here is that the derivative with respect to x of the natural log of x is simply 1 over x. So there's our rule for the natural log. And we can extend this with the chain rule. By the chain rule, what we have is that the derivative with respect to x of the natural log of y will be 1 over y times dy over dx. Okay, so basically what we did to find the natural log rule is we used what we know about e to the y, what we know about the exponentials, and used implicit differentiation. There are many rules out there that we can do that with. Right? We can actually set up lots of complicated rules using implicit differentiation. Okay. All right, so that's that rule. So let's do some basic examples. If I had y is equal to 3 natural log of x, okay, then dy over dx would be 3, the constant comes along for the ride, times 1 over x, which is 3 over x. Simple enough. How about one that would involve the chain rule? Let's say we have y is equal to the natural log of, let's say 1 over 3x squared. Okay, so the derivative, well, the derivative of the natural log of y, of stuff, is 1 over y times the derivative of y. So in other words, the derivative with respect to x of the natural log of stuff, okay, is basically 1 over the stuff times the derivative of the stuff. Okay. So this is going to be 1 over 1 minus 3x squared. So the derivative of the natural log of anything is going to be 1 over that anything. Then I'm going to multiply by the derivative of what's on the inside, or what's on the bottom there, which is going to be negative 6x. Okay, and this we would definitely want to simplify. This ends up being negative 6x all over 1 minus 3x squared. So basically, what happens is the derivative of the natural log of stuff ends up being the derivative of the stuff over the stuff left alone. So that's one way I like to write this rule. I find it very helpful, is that if you're taking the derivative, let's say, yeah, the derivative with respect to x of the natural log of stuff, it's going to be the derivative of the stuff over the stuff left alone. Okay. Another way to write this, let's say I wrote it with y's. We already have that, but with y's, it would be the derivative of y over y, which doesn't look great with fractions. A better way to write this would be the derivative of the natural log of, let's use f, okay, is going to be f prime over f. Okay, so that actually simplifies things quite a bit, so that if I have, I don't know, y equals the natural log of x squared plus 3x plus 10, the derivative of that, well, it's just going to be the derivative of what's inside, 2x plus 3, all over that stuff left alone. Right, not too shabby, right? Okay, now that we have this, we can actually start looking at furthering, furthering both of these rules, the exponential rule and the logarithmic rule, ln, to any base that we might want. Okay, so let's take a look at that. Okay, So here's the natural question. If the derivative of e to the x is itself, what about the derivative of 2 to the x? Or, say, 1/3 of the x? Or, more generally, b to the x. Any b. Okay? And the answer, well, we're going to use implicit differentiation. Okay, so we'll use implicit differentiation. So, and we'll start with, so let's let y equal let's do 2 to the x. Let's actually use a a number to start with. Okay. Now, I can't just take the derivative because I don't know what the derivative of 2 to the x is. So let's take the natural log of both sides. Okay, so I'll get the natural log of y is equal to the natural log of 2x. All right, and using logarithmic rules, I know I can bring that power outside. So what I have is the natural log of y is equal to x times the natural log of 2. Okay, now we can use implicit differentiation. Right, because this is just x times a constant. This, okay, this is, well, we know that the derivative of ln y is going to be the derivative of y over itself, or 1 over y times the derivative of y. So when we take the derivative of both sides, we get 1 over y times the derivative dy over dx is equal to, well, the derivative of x times a constant is just going to be that constant, ln 2. Okay, so I'm going to move the y over, okay, to get dy over dx, that's what I was looking for, is equal to y times ln of 2. And what was y? Well, if we go all the way back, y is 2x. So I'll put that back in. I get 2x times the natural log of 2. Okay, so there's our answer. The derivative with respect to x of 2 to the x is itself 2 to the x times the natural log of 2. Oh, so maybe the derivative with respect to x of 1/3 to the x is itself times the natural log of 1/3. If you thought that or guessed that, you would be absolutely right. It is. Okay. How about the derivative with respect to x of 16 to the x? Well, go ahead and guess. Following this pattern, yeah, it would be 16 to the x times the natural log of 16. So if you're ever taking the derivative of anything to the x, like a number to the x, like b to the x, any base, it's just going to be itself times the natural log of the base. Okay. So, and I'll tell you that you've been doing this entire time, you just haven't realized that, because the derivative of e to the x, if we use this pattern, say it's itself times the natural log of the base, well, the natural log of e is 1. So if you just always do that, you'll always get the right answer, whether it's e or not. Okay? So this brings us to the generalized exponential rule. Which basically says that the derivative with respect to x of b to the x is the natural log. Well, you can put it on the outside if you want, but it's itself times the natural log of the base. And if we extend it using the chain rule, b to the y, that's going to be b to the y times the natural log of b times dy dx. All right, so it follows the same process as e to the x. Only thing you have to make sure you do is throw in an ln b. So a lot of people will throw that in the front. It's ln of b times b to the y times dy dx. It doesn't really matter where you put it, wherever looks best. Okay, so let's look at some examples of this. Okay, let's say I have y is equal to 5 all to the x squared. So the derivative of 5 to the stuff is going to be itself, okay, times the natural log of the base. So that's always going to be there. Then times the derivative of the stuff, all right, which will be 2x. So this right here is the derivative of the stuff. All right, how about we have 1/2 to the 1 minus 3x plus 6x squared to get started. Okay, well, the derivative of that is going to be itself 1/2 to the 1 minus 3x plus 6x squared. So remember, if I have 1/2 to the stuff, that's what this is, its derivative is going to be itself times the natural log of 1/2 times the derivative of the stuff. So I have itself times the natural log of 1/2 times the derivative of the stuff. So this will be -3 plus 12x. Okay, let's look at another example. Okay. Let's say I have f of x is equal to 7 to the tangent of x. So when I take the derivative here, remember the derivative of 7 to the stuff is going to be itself, okay, times the natural log of 7 times the derivative of the stuff, right, which is going to be secant squared x. Okay. All right, let's try another one. Let's say I have let's say f of x is equal to let's say 1/5 raised to the cotangent x plus e to the x in the exponent. Okay, so the derivative of this, well, remember, all I'm thinking here is this is 1/5 to the stuff. Okay, 1/5 to the stuff. So this will be itself okay, times the natural log of 1/5 times, now I'm going to throw in the derivative of this stuff. Right, so the derivative of cotangent is negative cosecant squared x, and the derivative of e to the x is e to the x. Okay? Now, keep in mind, this is the same thing we've been doing so far. This is just like the chain rule with e to this stuff, except the only thing you're doing is you're throwing in an extra piece here. That's it. Don't overcomplicate this when you're trying to do it yourself. Seriously, it is just this simple. It's just like e to the stuff, except you throw in that natural log of the base. That is it. That's the only difference. Okay? All right, so we've talked about general exponentials. What about log base b of x, right? What about when the log is applied with a different base? And this one is kind of similar. Let's say I want the derivative with respect to x of, let's say, log base 2 of x. Okay. Well, to do this problem, we don't even have to do implicit differentiation or anything like that. We just use one of the log rules we have, which says that I can rewrite any log I want in terms of ln, or any log I want in terms of log base 10, or any other log. So log base 2 of x, I can actually rewrite as ln of x over ln of 2. Okay, which will be, let's rewrite it like this. This will be the derivative with respect to x of 1 over ln of 2 times ln of x. Right? So what we basically just have is a constant out front with an ln of x. So the derivative of this is just going to be 1 over ln of 2 times the derivative of natural log of x, which is 1 over x. So it ends up being, when I multiply this together, 1 over x times ln of 2. So this goes on to satisfy a similar pattern as before. So rewriting what we have, the derivative of log base 2 of x is simply 1 over x times the natural log of 2. Okay, what we're basically doing is just throwing in the natural log of the base. It's like what we did with, say, 2 to the x, except now, instead of multiplying, it's going underneath the fraction. So if I wanted to take the derivative of log base 3 of x, it would be 1 over x with the natural log of 3 on the bottom. Okay, so if I wanted to do log base 1/5 x, that derivative would simply be 1 over x times the natural log of 1/5. Pretty similar, right? What if I just said log? Log is which base? That's something you should definitely know. Well, this will end up being 1 over x times natural log of 10. All right, and then if I have any base, a general base, log base b, for example, that's just going to be 1 over x times the natural log of b. Right, so that's basically the generalized exponential rule in a nutshell. Okay. I think I said exponential. It's a generalized log rule. basically, if I have the derivative with respect to x of log base b of x, it's 1 over x with an ln of b thrown in as well. So just like with the exponential, if you have a different base other than e, you throw in an ln b. Okay. And if you want to extend this with the chain rule, you have log base b of y is going to be 1 over y times the natural log of b underneath the fraction, and then times the derivative of y with respect to x. Right? We can also write this as, let me write it like this. Think of this as y prime over y times the natural log of b. So same thing, same pattern, you're just throwing in a natural log of b underneath as well. Sorry about that. Okay. So that's our generalized log rule. Let's look at some examples using this. Okay, let's start simple. Y is equal to log base 2 of 1 minus x squared. So remember, derivative of log of anything is going to be the derivative of the stuff. So derivative of the stuff is negative 2x. So here I'll put derivative of the stuff all over the stuff. Now, since this is a different base, I now have to put in ln of 2. Okay, and that's it. All right, so let's make one a little more complicated. Let's say I have a log base 13 of, let's say, x cubed plus 3x squared plus 16x plus 11. So the derivative of that, well, is going to be the derivative of the stuff goes on top, so it'll be 3x squared plus 6x plus 16 all over, and we just copy down the stuff. And since this is a base other than e, we have to put natural log of the base. Okay, fair enough? Okay, let's try something like this. Let's say we have a log of tangent squared x. Okay, now typically this would be a pretty complicated chain rule because we have log of stuff and this is tangent squared, so that's stuff squared within it. But the beautiful thing about logarithms is that I can use this exponent rule, right, to bring that outside and give me 2 log of tangent x. And now when I take the derivative, it's just going to be, well, the 2 stays on the outside, okay? Then the derivative of log, well, it's going to be the derivative of the stuff, so the derivative of tangent, which is secant squared, all over the stuff left alone times ln of 10, since this is a base other than e. Okay. All right. So we could simplify this a little further if you're interested. Let me move the constant outside because this is essentially 1 over secant, or excuse me, 1 over cosine squared all over cosine over, sorry, wrong one, all over sine over cosine. So you can actually flip this around and get 2 ln 10 times 1 over cosine squared x times cosine x over sine x. Okay, which ends up being 2 over the natural log of 10 times 1 over cosine times 1 over sine. Well, that's going to be secant x cosecant x. Okay, which looks a little nicer than what we had here. Again, if you're, especially with trig functions, if you're checking your answers in the back of the book, you're going to get some things that might look like this instead of what you were expecting. Fair enough. Now, what we did here is we used log rules to actually help simplify what we were trying to do. Okay? That's a very useful tool. In fact, it actually helps us a lot. Let me show you some more examples where we do that, where we use logarithm rules to simplify the problem. Okay, so for example, let's say I have y is equal to the natural log of 2x cubed times sine of x. All right? Now, you could go about doing this just brute force if you wanted to. Right? You could say that the derivative of y with respect to x is the derivative of the stuff, which would be a product rule, okay, over the stuff if you wanted. Or a simpler way would be to simply use logarithm rules, right? We have 3 things multiplied together, so we could actually split that up as the natural log of 2 plus the natural log of x cubed plus the natural log of sine. And then, further, we have x cubed here. We could actually bring that power out front, so we have the natural log of 2 plus the 3 times the natural log of x plus the natural log of sine. Okay. Now when we go to take the derivative, it's just 3 simple pieces. The natural log of 2, that's a constant, so that'll be 0. 3 times the derivative of natural log of x, which will be 1 over x, plus the natural log of sine of x, okay, which will be the derivative of sine, which is cosine, over sine, left alone, and this ends up being 3 over x plus cotangent x. Okay. Much easier than trying the long way, which would be apply the product rule, right, which would be 6x squared sine x plus 2x cubed cosine x all over 2x cubed sine x. Now, if you fiddle with this enough, you will actually get this same thing. Now, you might think for this one, actually this was a lot less work than here. Okay? But that's not always the case, especially when you have quotient rules. So let's take another look at this next example, which we'll use a quotient rule. Let's say I have y equals the natural log of 2x minus 1 all over cosine squared x. Okay, now if you tried to do this the long way, right, it would be 1 over this stuff, which is already a fraction, times the derivative of this stuff, which would be a quotient rule with a chain rule on the inside, which is nasty. So instead, let's just break this up. I have a quotient, so this will be the natural log of the top minus the natural log of the bottom. And cosine squared x, well, remember that's the same thing as cosine x squared, so you can bring that power out front. I want to note that if this was cosine of x squared, you couldn't do that. Okay? Couldn't do that. So this ends up being the natural log 2x minus 1 minus 2 natural log of cosine. Okay? So when I take the derivative, I'll get, well, the natural log of 2x minus 1 will be the derivative of this stuff, which will be 2 over itself, 2x minus 1, simple enough, minus 2 times, now the derivative of natural log of cosine of x will be the derivative of cosine, which is negative sine, over itself, cosine. Okay, so if we were to simplify this, we would get 2 over 2x minus 1 plus 2, and sine x over cosine x is tangent. Okay, so way easier than trying the 1 over 2x minus 1 over cosine squared x and then using the quotient rule here, which would be 2 cosine squared x minus 2x minus 1 times 2 cosine x sine x all over cosine to the 4th x. Now I did that really fast because it's way better to do it this way, and I did it really fast, so I made a mistake somewhere. I did, because that should be minus sign. There's no reason to mess with this when you can just break things apart using logarithm rules. Okay, here's a prime example. Here's y equals the natural log of x cubed times the square root of 1 minus 6x squared all over e to the 3x times 2 plus x raised to the 5th. If you wanted to do this the brute force way, this derivative would be 1 over this thing times the derivative of this thing. Now think about the derivative of this thing. This is going to be a quotient rule with a product rule on the top and a product rule on the bottom, and within each product rule is going to be chain rules. Okay? This is going to be a nasty if you try to do it that brute force way, where it's just 1 over the stuff times the derivative of the stuff. What we're going to do instead is break this up using log rules. Okay? So this is really going to be, and I want to make sure I have plenty of room here, I'm going to break everything up. So what I basically have is, there's a lot of ways you can do it, but let's start by saying that I have, let's break up this fraction on the inside. Right, I have x cubed over e to the 3x all times this one. So that's a good first way to do this, because when I have two things multiplied together, I can have natural log of x cubed over e to the 3x plus the natural log of the square root of 1 minus 6x squared all over 2 plus x raised to the 5th. And now I can split this up even further, because this will be, now that I am dealing with quotients, I can break those up with subtraction. So this natural log of x cubed minus the natural log of 3x plus the natural log of the square root of 1 minus 6x squared minus the natural log of 2x plus, or 2 plus x raised to the 5th. Okay, and I wrote this wrong. This is e to the 3x, not 3x. Now, I can start taking out powers, right? x cubed here, I can take that 3 out and get 3 natural log x. Natural log and e will cancel, and this will just be 3x. What can I do here? Well, as you all know, this square root is actually a half power. So if I go back and rewrite this as to the half power, I can take out a 1/2, have natural log of 1 minus 6x squared, and then here we can take out a 5 and get 5 natural log of 2 plus x. Alright, so kind of running out of room here. Let me grab another sheet of paper. Okay, so now we have simplified this as far as it can go, because if I have sums or differences within the natural log, I can't actually break that up. Okay, so the derivative, well, the derivative of 3 ln x is going to be 3 over x. Derivative of negative 3x is negative 3 plus 1/2 times, now this will be the derivative of the stuff, which will be minus 12x over the stuff. Okay. Then minus 5 times the derivative of this stuff, which will be 1 over 2 plus x. Okay. And there we go, that's the derivative. We could simplify this a little bit. Right, this 2 will cancel with the 12 and leave a 6. So I could maybe say that this is 3 over x minus 3 minus 6x over 1 minus 6x squared minus 5 over 2 plus x. And there we go. Okay, much simpler than trying to do 1 over this mess times the derivative of it. Okay. Now some of you might be thinking that, man, this whole thing with the logs where we can split up the log instead of doing all these nasty derivative chain rule kind of things, you might think that's really nice, and you might think, I wish I could use that on things that I don't have a logarithm, right? Wouldn't it be nice if, say, instead of, you know, those problems where we have product rules within quotient rules, chain rules all together, and they become this really sort of big chore to get all the pieces together. You might think, well, wouldn't it be nice if I could use that idea with just breaking it up with logs on all the problems? And for many problems, it's not worth the trouble, but for something like this, say I have x to the 5th times e to the 2x times sine squared x over 1 plus 6x all squared times the square root of secant x. This would be disgusting to try and do by, right, just to take the derivative, because it's going to be a quotient rule with a triple product rule at the top, chain rule, and a product rule on the bottom, 2 chain rules. Really unpleasant. But we can use what's called logarithmic differentiation. I believe is what the book calls it. I don't know if there's really an official name for it. Basically, what you do is you take the log of both sides, okay, and use implicit differentiation. Okay. So you're going to take log, or actually ln of both sides, I should say. And use implicit differentiation. Okay, so basically we will have the natural log of y is equal to the natural log of all this junk, x to the 5th, e to the 2x, sine squared x, all over 1 plus 6x squared And I'm going to write this as secant x to the 1/2 because that's how we're going to use it. Okay, then what we get is if we break this up, we get that natural log of y. I'm going to keep writing that because that's important to what we'll have. Is going to be, now a quicker way to break this up, anything on top is going to be a plus, anything on the bottom is going to be a minus. Okay, now I'm going to go ahead and take the powers out all in one go. So this is as quick as you can do this. If you need to do this in more steps, that's fine, but check out how fast I can do this. This is 5 ln of x plus 2x ln of e, which I know is 1. Okay, so I'll just write it's 1 plus 2 ln of sine x, okay, minus, I'll start the minuses down here, minus ln, and there should be a 2 outside, so minus 2 ln of 1 plus 6x minus 1/2 ln of secant x. Right? Doesn't take that much. Once you get the hang of this, it's pretty simple. So now I'm going to use implicit differentiation, which means using implicit differentiation, derivative of ln y is going to be 1 over y, dy over dx. And I'll have derivative of 5 ln x is 5 over x. Derivative of 2x is 2. Derivative of ln of sine, and I have a 2 out front there, is going to be cosine x over sine x, right? The derivative of the stuff over itself, minus 2 times the derivative of ln of 1 plus 6x, so that will be the derivative of the stuff, which will be 6 over 1 plus 6x, minus 1/2, and it will be the derivative of secant, which is secant x tangent x over itself, which will actually cancel. Okay, so there we go. There's that, and let's put this up. Now, remember, implicit differentiation, you solve for dy over dx, so I'm going to move that y over. It'll be y times, and then I'm going to simplify what's in here. It will be 5 over x plus 2 plus 2. Cosine over sine is cotangent x minus 12 over 1 plus 6x minus 1/2 times tangent of x. Okay, and then the only thing you really have left to do, basically the answer, is you can put your y back in. If you remember what the y was, it was this big nasty thing. You can put that back in, and that will be the derivative. Okay, so the derivative dy over dx will be x to the 5th e to the 2x sine squared x over 1 plus 6x squared times the square root of secant x, and then times this thing, 5 over x plus 2 cotangent x minus 12 over 1 plus 6x minus 1/2 tangent of x. And there we go. Okay. Yeah, it's kind of a complicated process. You're using implicit differentiation, but it's actually a lot better than trying to take the derivative of this thing using the quotient rule with product rules, chain rules, and all of that. Alright, so that's all I really want to talk about today in this section. What I will say is, with this logarithmic differentiation, give it a shot on some of the problems that you've done before. You've had two worksheets I can think of where you've had a problem where it was product rule within a quotient rule. And try it with the logarithmic differentiation and see if you can get the same thing out. Your answer is going to look different both ways, but see if you can manipulate it using algebra to get the answers to look like one another. In fact, that would be a good test to see if your algebra skills are where they're supposed to be, is if you can get from one answer to the other. One way using logarithmic differentiation and the other way using just your typical brute force, quotient rule, product rule, chain rule. Okay? All right, well, the next lecture we will be looking at another application of implicit differentiation. And so I will talk to you all then. Cheers.